Good morning, everybody. Thanks for coming, especially at this time. So today I will tell you a story of functional synchronization as we see with MEG. And the starting part of my talk won't be related to the definition of resting state. I will actually start a little further ahead from functional cores. So we know that the functional connectivity is characterized by these functionally specialized systems which dynamically integrate. And in this integration, cortical hubs play a fundamental role. And they are, on one side, densely connected with the rest of the brain, but at the same time, they seem to talk to each other. And this is very interesting, because this idea of functional hubs being connected among themselves gives rise to a set of new models of integration that I think are very interesting. In particular, in these new models that we call core networks, basically networks built on functional hubs, two fundamental ingredients are really important: the spatial topology on one side and the specific temporal dynamics. These two ingredients may make overall an efficient integration process. So let me start with the first model of spatial topology from a very influential paper, Van der Heuvel and Sporns, the rich club, the idea of a rich club. So basically the message is pretty clear. From a structural point of view, if you take DTI data, and you realize that nodes reaching structural connections, they tend to be linked to similar nodes rich in structural connections. This horrible metaphor of rich club where rich people like to be with rich people. Exactly the same. Structural hubs, they like to link with other structural hubs. And this is the first example of a spatial topology driven by structural data. But when you take into account the functional connectivity, and in particular the temporal dynamics of the functional connectivity, you realize that some of these hubs, for example, in the structural core, it was identified the precuneus, the anterior and posterior singular cortex, superior frontal cortex, and many other nodes. Well, a similar set of nodes you can identify using MEG and looking at the functional coupling and taking into account the temporal dynamics of this functional coupling. So what we observed is this dynamic core network, where you basically have a set of functional hubs alternating their centrality over time, being strongly connected with each other, but at the same time giving rise to this dynamic core of integration. The set of hubs nicely overlap with some regions identified, for example, with the rich club, the posterior singular cortex again, the supplementary motor area, and the right posterior intraparietal sulcus. So one big question is, okay, but why the brain should adopt such a dynamic strategy of integration? Does that correspond somehow to a global optimization criterion? Well, when you look at the connectome and the dynamics of this connectome, and you take into account the global efficiency of the overall connectome, then you realize that there are moments in which this efficiency is higher, and these peaks of efficiency somehow relate to the temporal epochs when you observe this alternation of centrality in your dynamic core. So basically the answer seems to be yes. This dynamic core somehow is optimizing the global efficiency of information transfer in the whole brain. These few nodes, they actually are able to cover up to 70% of these global efficiency peaks that you're observing. But so far, I have to be honest, I've been a little vague. I somehow defined this dynamic core. I said that these hubs are alternating over time, but I didn't say much on the actual temporal structure of this dynamic core. What happens inside the dynamic core? Do we have nodes really independently alternating over time? Do we have nodes synchronizing one with the other? And what happens to the efficiency, to the global efficiency? to these possible scenarios that we want to investigate. So to this aim, to address these questions, we actually start again with a large set of data. We have now 105 resting state sessions. We have a much denser parcellations as compared to the one that we used before. So we move from a 46 parcellation to 155 node parcellations. We included 9 resting state networks: the default, dorsal and ventral attention network, somato-motor network, the language, the auditory, frontoparietal and control networks. We applied an accurate signal leakage correction by means of the geometric correction scheme by Vincent Vance. And more importantly, we look at the temporal dynamics in a spontaneous way. I mean, we sample the temporal dynamics at 5 Hertz every 200 milliseconds, but we did not select any temporal epochs, okay, as we did before based on the MCW selection. So we just keep all the temporal epochs one after the other. This is how we sample the dynamics. Well, if you do that, and you look at the between centrality of your nodes, this is what you get. So these, over time, are the functional hubs, the regions that are consistently more central. We have some nice overlap with the previous regions that we observed. We still see the supplementary motor area. We still see PCC and many variations around it, precuneus. We see a lot of visual nodes, but also we have some additional nodes from the frontoparietal network, for example. So we have some overlap, but this is the largest set of functional cores. This set of hubs is frequency specific. If you move into the alpha band, for example, you get less nodes, fewer nodes, okay? But now let me go to the most interesting part. Once we identify these consistent hubs, we want to look at the dynamics of your centrality. So what we did is that we take every single hub, we extracted the centrality time course over time, and then we compare these temporal dynamics of centrality in order to identify, if any, a synchronization for every pair of hubs that we considered. So we did that using the synchronization accuracy, and then, so in this way we obtain a synchronization matrix, and then from the synchronization matrix we applied a K-means algorithm to find if there was an optimal number of clusters identifying synchronized structures within the dynamic core. So K-means tells us that the optimal number of clusters is 3, and we call these clusters dynamic synchronization modes, meaning that one synchronization mode is actually a set of functional hubs being consistently central at the same moment of time. They go up and down together. So this was the original set of hubs, you see. And the synchronization modes that we identify are this one here. So black nodes are those hubs that they have a dynamics, but this dynamics is actually unrelated to the dynamics of the other hubs. They are independent. They have their own dynamics, and there was no evidence of any synchronization with any other regions. Instead, we obtain a green synchronization mode, as you can see, and blue and a red one. And the green one, I think, is one of the most important because, as you can see, it's formed of parts of the default mode network, the frontoparietal network, somato-motor network, and the language. And first of all, they are not, I think, in this movie, you see the dynamics and how they alternate over time. So by definition, by construction, these synchronization modes are alternating over time. When one is up, the other one is not, and so on and so forth. And as you can see, the green one represents, I think, an important axis of integration between networks related to functional cognitive domains, like the internal cognition of the DMN, the cognitive control of the frontoparietal, the motor planning of SMN. And I think it's interesting, this idea that this integration among such important domains happens through synchronized functional hubs. We previously observed something in that line. We observed a strong interaction between PCC and SMA, but now the scenario is enriched by these front-of-horizon and language nodes. Another important result, I think, is the PCC parcels. I mean, PCC precuneus, although some of these regions are really close to each other, when you use the temporal dynamics of centrality, then they split into two different subgroups. And this is somehow related also with some previous results based on the eigenvector centrality. And the final message is that this mechanism, this temporal mechanism, is actually frequency specific. When we look at the alpha band, that is a band very close to beta, well, we didn't observe any evidence of synchronization. This seems to be specific for the beta band, or at least. So far we analyzed alpha and beta, so that's all I can say now. Okay, now if we go back, if you use the similar outline to the previous work, let's have a look what happens to the efficiency now. Well, when we look at the efficiency of these sync modes, we realize that the efficiency, the global efficiency, during these synchronization mechanisms is actually higher than outside. So if you take the temporal epochs in which you have this high synchronization, then the global efficiency is higher than outside. And the global efficiency is pretty similar across the synchronization modes. They are all equally efficient. And another important message that I want to highlight is the vulnerability. So if you take, for example, the first synchronization mode, that is just 5 nodes out of 155, 3%, you remove those nodes. You replace these nodes with the same number of random nodes. So basically, you are removing this temporal mechanism of synchronization, while the vulnerability is 30%. That I think is pretty amazing, given the small number of nodes that you are removing from your connectome. So your connectome is really strongly affected by the removal of such temporal and dynamic integration mechanism. A final question that we might address is, okay, but what happens during this synchronization? So what happens to the connectome when you have this mechanism? Who is talking to each other? So if you take synchronization mode 1, and you look at the structure of connectivity, of functional connectivity, but the architecture of this functional connectivity among the networks, this is what happens. You see that the visual network, this mouse doesn't move much, okay. The visual network is actually left somehow aside, and this is what happens with the other synchronization mode. So, yeah, probably there is a little difference, but you know, averaged across the networks, I wouldn't say much. But when you go back to the dense connectome, I think another important message is coming. Look what happens. This is the dense connectome average during the synchronization mode 1. And you can clearly see here that you probably have 2 big functional modules, highly integrated, 1 and 2. In fact, when you run the functional modularity, the Louvain modularity, the highest modularity you get is when you have 2 communities. And interestingly, these bright stripes here are the functional hubs. So you can see that the functional hubs are actually integrating those 2 big modules. Look what happens during synchronization mode 2. The structure is different, completely different. Now it seems like that everything is more segregated, and the highest modularity is obtained when you have 6 functional modules. And again, the bright stripes, these bright rows and columns, they correspond to the functional hubs. I need to stress something here. These 2 configurations, these 2 architectures, they correspond to the same global efficiency. So one big question is, how is that possible that such different spatial architecture actually gives rise to the same global efficiency? And again, the answer, I think, is in the dynamics of these functional hubs. So when you look at the dynamics of these functional hubs during those temporal epochs, when you average the connectomes, you realize that, for example, for the sync mode 1, your functional hubs they really split among the two modules. You see the number of connections they have in the two modules is around 50%, are equally distributed, more or less. And the participation index for sync mode 1 is around 50%. So they have the same number, the same exact number of proportion of connections within and outside the modules. But this is even more true for the sync mode 2. When you look at the participation index of sync mode 2, I don't see the mouse, but anyway, when we look at the participation index in sync mode 2, you see here that the values are extremely high. I mean, you get as very close to 0.8, 75, 70%. So this means that basically this makes the trick for sync mode 2. Sync mode 2, that from a spatial topology seems more segregated, is actually equally integrated, equally globally efficient as sync mode 1, thanks to this extreme dynamic integration performed by the functional hubs that somehow balanced the potential spatial segregation. So just to summarize, I hope I convinced you that cortical hubs are important and they are organized in these super networks, and the temporal dynamics is fundamental in this integration. We observed a set of hubs alternating their centrality. This alternation and this mechanism seems to correspond to an optimal global optimization criterion. But when you look at the temporal architecture within the dynamic core, then you realize that hubs can be classified into independent hubs. They have their own dynamics, they go on their own. And some of the hubs are instead synchronized. And when you look at these synchronization modes, you have a nice axis of integration across important functional domains like the DMN, frontoparietal, and somotomotor, related to the internal cognition, cognitive control, and motor planning. And again, when you look at the spatial architecture during this synchronization, you realize that different spatial topologies can be equally efficient thanks to the extreme effort of the temporal dynamics of the involved functional hubs. So I need to thank my own special, very special core network, and thanks a lot for your attention.